Hi, everyone. My name is Cara Peterman, and on behalf of CFSEI, it's my pleasure to provide some video explanation for Tech Note G900-23, which provides a design methodology for reinforcing holes that may appear in cold-formed steel beams. So this is just a screen cap of the first page of the Tech Note. We're not going to spend a whole lot of time here, but I did want to point out that very early on, the Tech Note is very specific to say if you have a member with a hole that hasn't yet been installed in a building, this is not the Tech Note for you. You should use the member with hole provisions in AISI S100. This Tech Note is when you have designed your beam for the full unreduced cross section, and you are relying on all of that strength to achieve capacity. Of course, we all know that sometimes holes are cut in the construction process, and this is the Tech Note for you for how to reinforce those holes to mitigate any ill effects the hole may provide. So again, if you are intentionally designing a member with a hole, AISI S100 provides design specification language for that. This specification is if you need to reinforce and get capacity back when a beam has had a hole cut into it. The Tech Note divides these types of holes into holes in the flange and holes in the web, and subdivides holes in the web into ones that may cause bending failure and ones that may cause shear failure. So I'm going to move quickly to some notes that might enrich your reading of the Tech Note, provide some additional context. So first off is that when we have a beam and bending, the full unreduced cross-section will have an elastic bending stress distribution as drawn here with a compression side and a tension side for positive bending. Remember the smiley face. And the Tech Note deals with two types of holes. Again, the pink is a hole in the flange, blue is a hole in the web. And so we'll go through each one of those step by step. For a hole in the flange, we are designing the reinforcement to resist the forces, those compression and tension forces that then combine into a force couple to create the moment on the section, the bending of the section. And so you need to design your whole reinforcement to resist this M, which is the C or the T force times the depth of the section, forming that force couple. And of course, the fasteners must be able to transfer to the remaining bits of the flange. So this is a fairly straightforward reduction from the bending stress distribution to the force couple because the flanges are at the extreme fiber of the cross section. So all of those elastic stress distribution concentrate to the force couples, and the flange reinforcement needs to be able to resist C or T. Web is a little bit more fun. First off, there are two failure modes involved. Can fail in bending or can fail in shear when you have this unanticipated hole in your web. Let's start with bending. The idea with the bending failure mode is that you would now like to reinforce your cross section right at the edges of your hole. Top and bottom, get as close to the hole as possible. And that reinforcement needs to be designed to resist the forces from the bending stress distribution that occur right at that hole edge. And again, we're using the elastic stress distribution as our basis. So let's take a look at this sketch I've drawn here. And so in black all the way at the left is your poor cross section with a big web hole. And remember, this hole does not need to be centered on the neutral axis of the cold formed steel member. I have drawn it here. It looks centered, but I've made the variable name such that it does not have to be. And a common reinforcement would be to use these little channels right on either side of the web hole. And if you study the diagram very carefully, the forces that you design those channels to withstand are F1 and F2, which are just slightly off of the actual edge of the hole. The full capacity, the full flexural strength of the reinforced cross-section is going to be the strength of the cross-section with a hole, and then the strength of the reinforcement. These area of the reinforcement, AR, times force, F1 or F2, times its distance to the neutral axis, D1 or D2. So again, forming that force couple, but again, you're allowing those forces to be unequal and to be different distances from the neutral axis, because that hole could be anywhere, realistically. This equation, I always think, is a little bit confusing when you first look at it because it says it has to be less than or equal to M without a hole. So the flexural strength of your beam with no hole fully unreduced. And you might think, well, shouldn't it be greater than or equal to? Isn't that how we design things? Well, no. I mean, the way to think about this is that the flexural strength of your member without a hole is the maximum it can possibly be. And so in reality, you are trying to get the left side of the equation to be equal to the right side of the equation. The Tech Note provides some really common cross sections where you might use those to try a candidate area of the reinforcement. You could, of course, also solve for the minimum area of reinforcement using this equation, because you will have MNO, F1, D1, F2, D2, etc. So that is a path that's not explored in the Tech Note, but is available to you. The design objective here, which will be contrasted by the design objective when we have a shear dominant case, is to achieve the bending strength of a cross-section without a hole. So loosely, we need to get the cross-section back up to the flexural strength without a hole. And then my final little note here for these bending dominant cases is that the Tech Note provides guidance on the actual length of the reinforcing section based on hole geometry. Let's discuss shear. So the interesting thing about shear is that most cold form steel beams are actually over-designed for shear. They have quite a lot of leftover shear capacity that is not needed. And this segment is predicated on not achieving the nominal shear strength via that reinforcement. So nowhere do we say, oh, the nominal strength of this unreduced cross-section in shear was this number and we need to get up to that. No. You instead try to get the most accurate prediction of shear strength possible, or the contribution to shear by the reinforcement, and compare that to the actual demand shear. So that's a key philosophical difference between the bending approach and the shear approach that I think is really important to keep in mind. There are two options. We'll start with the first option, and this is how I've distilled these calculation steps. The design guide takes you through these and provides calculations in full for these. In option one, this is where you say, you know what, I'm not going to consider the contribution of the reinforcement. I'm going to take that overstrength in shear in mind and just see if my section without with a hole in it has enough strength. So you do your reinforcement as you need for bending strength. You still need to do that. You still need reinforcement. But when you calculate the shear capacity of the cross section, you assume it has a hole. You do not consider reinforcement when you calculate the shear capacity. You say whatever it needs for bending is enough for shear. I'm going to make sure that the remaining part of my cross section can hold the required shear strength. So in step 3, you compare to your shear demand and increase your area of reinforcement if you need to. That's option 1. Let's talk quickly about option 2. Option 2 is where you're going to do a soup to nuts design of the reinforcement. And so you're going to take your little channels that you have in mind that you might need for bending, and you're going to design those as a flexural member and calculate the shear strength per AISI S100 section G2 of the reinforcement. So you are doing all these calculations on these little itty bitty reinforcing members and calculating the shear strength of those. Now you have what the additional capacity is once you added the reinforcement in, and you can compare that to the required strength of the beam in shear. Once you have that and you have sized your reinforcement accordingly, then you need to connect the thing to your section, and which you would do according to shear flow. So VQ over I to design that fastener spacing. The Tech Note gives you some guidance in terms of what fastener size to use, so that's really the only thing you need to consider, and provide suggestions as to the fastener spacing as well. So with that, that is Tech Note G900. I hope you have found this useful in your careers as cold form steel engineers. Thank you very much, and we will end it here.